Okay, within the gravitation unit, something happens where when we talk about energy, and one of the ways that we used energy in the energy unit was we talked about potential energy being equal to change in potential energy being equal to change in mgh, where the height was above some reference point. So that was true, mgh. Again, if we picked a reference point, we don't have to have the delta in there. Potential energy equals mgh above some reference point. And that allowed us, this was a stand-in, a substitute stand-in for the work done by gravity. Because we know work equals change in kinetic energy, but we get really tired of doing the work done by gravity all the time in these things. So it's sometimes easier to use this and then say mechanical energy is conserved. Total mechanical energy equals total mechanical energy prime. Okay, so that's why we had potential energy equation. It's not a real energy. I could hold this pencil up and I could say it has zero potential energy relative to my hand, or some small potential energy relative to the table, or some big energy relative to sea level, or some negative potential energy relative to the second floor. So what I choose for my reference point is really depends on what kind of problem I'm trying to solve. And any problem with that potential energy, you're usually just trying to find kinetic energy at some other location, or how much work was done by some other force. So it's these are just relative. It's very relative to reference point. Okay, and I'm going to do a couple of little things. Here we go. Here's the pen, and I've got some height above the table. Here's the ceiling. I've got some negative height there. So if this is my reference point right there, U equals 0. If this is my reference point, U of the pen would be mg times that h. And if this is my reference point, the U would be equal to mg times some negative number. I'll just call it negative h. Okay, so it'd be negative number. So having a negative potential energy that's okay. We just use it with this conservation of energy business to solve problems. We don't. It's not an end all. It's not a real energy. Okay. Now, when we start talking about this is linear. Okay. So if I raise the pen up 1 meter here, my potential energy would change by the mass of the pen, the weight of the pen, actually, mass times g times 1. Well, if I'm very, 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 very far away from the Earth, the gravitational field is a lot smaller. So instead of mg, I really have to use that gravitation formula. But it's a little more complex. Remember, this is standing in for the work done by gravity. And I'm not going to show how that goes. I'm simply going to say that this is more for AP Physics 1. You have to do an integration, by the way, to figure out how much work is done by gravity when you're moving at some distance far away from the Earth's surface. When you're close to the Earth's surface, it's linear, and we can use this. But because we know how the work done by gravity just ends up being mg times the change in height. So it ends up being equal to that change in potential energy. Now let's look at the planetary case. Okay, so let's just say you've got Earth here. And we know as you go up in that direction, U increases, right? U gets more positive as you go higher and higher and higher and higher. Well, let's pretend we go infinitely far away, right? If U is continually increasing, it doesn't make any sense to have this infinitely huge potential energy up here, right? Because if that were true, then things happening on the other side of the universe would have to take into account potential energy relative to the Earth. It doesn't make sense. Similarly, if we got some planet over there and we're infinitely far away over here, we'd have, I drop a ball near Earth. We have to take into account the infinite potential energy at this great distance. So it's convenient for us to call this potential energy the reference point, infinitely far away. Okay? The reference point, infinite distance. Okay? That's our reference point. And we're going to call it, again, since the U increases all the way up there, if this is 0, U equals 0 up here, then it must be getting more and more and more and more negative as you get down here. So the characteristics of this, and let me just write it down, is the potential energy, gravitational potential energy, in the more exact way, is going to get smaller and smaller and smaller as you get further away. So it's going to be proportional to something with a function of r. And it's going to be negative. Again, because if this is 0, and we know the potential energy has to increase as you go farther and farther away, then this must be negative down here, closer to the Earth. And the way this expression goes, and again, you can integrate the work going from point A to infinity, from a certain point to infinity. You can, if you do that, you can calculate what the change in potential energy is, and then we get this. So we talk about this being the gravitational potential energy of an object relative to another object at some distance r from that object, with assuming potential energy is 0 at d equals infinity, infinitely far away. It's a weird thing, but you get used to it. Okay, so this is the assumption all the time for these energy calculations that we're going to be doing. And I apologize that the light keeps shifting so much. I need to lower the blinds a little bit so it's a little more consistent. Okay, so this is the equation we're going to use. Well, guess what? We're just doing the exact same stuff that we did before. Total energy equals total energy prime. And then generally it's just potential plus kinetic before equals potential plus kinetic after to solve problems. Now the numbers are going to be ugly because we're dealing with a whole lot of scientific notation, but let me show you what it looks like. I shoot a bullet, I'm going to say I shoot a bullet up. It's a magically big bullet and there's no air resistance from Earth surface. And velocity initial is going to be, I don't know, I'm going to make it 10,000 meters per second. Okay, and the bullet's mass, just to make it easy, it's a 0.1 kilogram. It's a big bullet. It's a big rock. Okay, I shoot a bullet up from Earth. And how high does it go? Okay. Now, this is a big enough number. If we're talking about, 10 meters per second or something like that, you're simply going to do, I'll just do it over here. E total equals E total prime, mgh plus 1/2 mv squared equals mgh prime plus 1/2 mv squared. And you know how we do this. We plug in our variables. At the very top, it has no velocity, so that is there. If we pick the ground as a reference, then its initial potential energy is 0, and we end up with an expression and we can solve for how high it goes. But when you do this, when you're talking about big, big velocities, all of a sudden it's going to be traveling some significant distance to the point where our normal mg doesn't work anymore. We have to use the gravitational equation. Well, that's all wrapped up in here. So again, if we're talking about just tens of meters per second near Earth, yeah, feel free to use MGH. But when we're talking about planetary distances, we want to start looking at using this instead. So let's do it. E total equals E total prime. Always write it. Conservation of energy, very, very important thing to say. Okay, so when we say how high does it go, that's really the altitude, but you'll see what happens here. So potential plus kinetic equals potential prime plus kinetic prime. Not MGH anymore. Negative G M1 M2 over R plus 1/2 mv squared equals negative G M1 M2 over R prime plus 1/2 mv prime squared. Okay, now at top, V equals 0, right? We're saying how high does it go? So this whole term becomes 0. At the bottom, this is not 0. We can't do that. This, at the bottom, this is the radius of the Earth. Okay, so what we would plug in, and I'm not going to solve it, but what we would plug in is negative 6.67 times 10 to the negative 11, right? And the negative is for this whole expression, times the mass of the Earth. I'm going to round 6 times 10 to the 24th kilograms. Use the real one. Times 0.1. I just want to show you what gets plugged in here. Times the radius of the Earth. About 6.37 times 10 to the 6th meters. And notice, no exponent. You're going to screw that up an awful lot. This looks an awful lot like the gravitational force equation, but there's no squared in the R. Okay? Plus 1/2 mv squared, 1/2 times 0.1, the mass of the bullet is the thing that's traveling, times 10,000, that's 1e4 squared, equals negative, and now I'm doing this term, 6.67 e minus 11 times 6e24. I'm going off the edge. Let me slide over. Times 0.1 divided by r prime. Okay? And this, notice, this is going to be the radius of the Earth plus the height. So once I get that r prime, that says how far it is from the center of the Earth. But we need to subtract out the radius of the Earth to figure out how high it went. Okay? So if you look, all numbers of one variable. You chunk out those numbers and you're going to get your answer, how far from the center of the Earth. Subtract out the radius of the Earth and you get how far above the center of the Earth. So that's a basic conservation of energy problem for shooting something up from Earth, for throwing something up in the air. But now we're using more exact numbers because the force of gravity changes as this thing gets farther away. So we have to use this new expression for potential energy.